Hello, my fellow organic chemists, and welcome to the Diels Alder reaction. I'm Duncan, and today I will be giving you a basic guide of this reaction, only focusing on how to reach its outcome. While there are many details that I could explain, I would like to more focus on the most important elements that will get you to being able to recreate the outcome. So, most important part, the diene and the dienophile. These are the two reagents that we're going to use in order to reach our product. Focusing specifically on the diene first, we must have it of the conjugated variety, which means there's one bond between the two carbon-carbon double bonds, which I've highlighted here. Now, another important quality is that it must be an S-cis formation. So you see how they are both on the right side of the single bond. That is very important instruction in order to cause the reaction of the with the dienophile, which in this case I'm just drawing an ethene. It's the most basic dienophile. Now, there are certain elements that can make the diene or dienophile more likely to react. These are called enhancers. On the diene side, there can be things called electron donating groups attached, EDGs. Now this can be a whole range of molecules, weakest one being alkyl group, the weakest. Not ideal. We would much rather have one of these other three. There are a hydroxyl group, or an amino group, or even an ether. All of these things will promote this reaction. And on the other side, attached to the dienophile, you could have an electron withdrawing group, or an EWG. This can be a whole sort of other molecules, including halogens. These are great ones. Carbonyl groups, which I will show in a little bubble. Is a double bond, oxygen to carbon, substituents off the carbon. Any of these will work. In addition, nitriles can also work. It has similar properties to carbonyl groups. In addition, and maybe perhaps the best, is a nitro group, which we may not have run into with many other reactions as this basic structure, and it's a very good electron withdrawing group. And now that we have our reagents in order, we can go on and do the entire reaction. Now, this reaction does require heat. However, that's the only thing besides the reagents. The two electron donating group and electron withdrawing group will promote this reaction. And here I show the mechanism for it. This is how the electrons move to create new bonds and create a cyclic molecule. However, there's some specific elements of the cyclic molecule that are important to note in order to determine what outcome we have. Because we have generated two new stereocenters, there are four possible outcomes of this reaction. So, first, in order to determine which one we have to look at each stereocenter and how the reaction takes place. Right now, let's focus on the dienophile, which I'm circling here, circling where it is in the product. Now, if I'll redraw it, except this time, I will draw the hydrogens that are coming off of the double bond. Now, specifically, I want to focus on these two, on what I label as hydrogen 1 and hydrogen 2. Let's see here. I'll write them down over here. It is important to note where they are on this molecule as it stands right now. As shown here, hydrogen 1 is on the same side as the electron withdrawing group. So they will be cis together. And it will translate over to our product. So, draw kind of the basic structure of what is important to know for this dienophile. Here I will put it on a wedge. It doesn't matter if it's on a wedge or a dash. Right now, I'm drawing it on a wedge. Now, hydrogen 1 will also be on a wedge. However, will be on a dash. Now, this is just one of the examples. The enantiomer is also true. So when the electron withdrawing group is on a dash, hydrogen 1 is on a dash, and hydrogen 2 is on a wedge. So let's move on to the diene. We're here, just the basic structure, along with the electron donating group. here, I will also draw the hydrogens associated with these. So I'll have hydrogen 1 be facing downward and hydrogen 2 facing inward. This is important to note for how the molecule is going to end up. Draw the mechanism one more time just to make it clear. So when this reaction takes place, and there will be heat associated with this, which is not pictured here, but is assumed based on the diagram above, happens with this is that our dienophile attacks the diene, one associated with the electron donating group, the electrons this way, and all back. And here we have made our cyclic compound. So this compound, and that you'll see with where the hydrogen 1 and 2 ends up, the direction at which it is drawn is vitally important. So we're going to say electron withdrawing group again on a wedge, doesn't have to be. We're saying that for this enantiomer, those two enantiomers will be formed. Electron donating group will also be on the wedge. This has to do with the position that it's at. Now, moving on to the hydrogens, because the electron donating group is facing up, away, and hydrogen 1 is also facing away, it will be facing the same direction, the end molecule. So it is on that wedge. Therefore, hydrogen 2 will be on the dash. This will always be how it is when we draw the molecule as we did on the left side, where hydrogen 1 is facing down. So, and this is a very cool little shortcut drawn. Both A's, and here I will just say the normal A is the electron donating group, they will both be formed the same side as the electron withdrawing group. So what this means is that when we create our cyclic compound, here I will again put on a wedge. It will be the same thing as the electron withdrawing group. So A will be the exact same thing. So that means that B on this diagram will be on a wedge. The same thing with A prime. A prime will also be on the wedge, and B prime will be on the dash. And of course, we must include the enantiomer, because we can flip this molecule, it will still be the same molecule, and there's no permission for that. So here I'll very quickly draw the enantiomer will look like. In this case, electron withdrawing group will be on a dash, which means that A will be on a dash, B will be on a wedge, and then that means that A prime will also be on a wedge, on a dash, and B prime will be on that wedge. Here is the full reaction, the full stereochemistry for the Diels Alder. Now, let me get on to some of the fun stuff, some of the stuff that's behind the scenes of some applications. Now here, we see this is an early step. The Diels Alder reaction is used to create cortisone and cholesterol. We see the dienophile right here on our first reaction, and we are reacting it with a diene. So we know what happens, it creates a cyclic compound. So, that will show. And just by the way, we can rotate a single bond. We can't rotate a double bond, we can rotate a single bond. In this case, this single bond to create in that cis formation to create the cyclic compound. Here I've just outlined it. Now, it can also be used in the original synthesis of a few prostaglandins. So, down here, we have the main reactant on the left is the diene, and we are reacting it with the dienophile reagent. And see here, I'm showing the cyclic molecule that comes out of it, and while I'm not specifically talking about how it gets created in a 3D fashion, which is important to note for this reaction, I do want to at least acknowledge the fact that it will have a preference towards endo. Thank you for listening. This has been Brief Review into Diels Alder.